Everyone, welcome back. This is lecture 11 of the lecture series Signals and Systems. In this lecture, we'll be learning about Laplace transforms and the region of convergence of Laplace transform and also about the inverse Laplace transform. So let's get started. So in the previous videos, we saw about the Fourier transform. So there we studied about these two equations. The analysis of the Fourier transform equation x of t e power minus j omega t dt and the inverse Fourier transform or the synthesis equation given by this one e power j omega t d omega. So you should be careful with the signs. Okay, so in this lecture we are going to see about Laplace transform. So first we'll find the motivation for Laplace transform. If you see Fourier transform, it is limited to signals which are absolutely integrable, right? Limited to signals which are absolutely integrable. So one thing is we want to extend this to other signals as well. So extend this to unstable systems also. So why system? Because if h of t is the signal, like it is the impulse response which is representing the system itself, so it will be useful to examine our unstable systems also. So for that also we require Laplace transform. Mainly it is to check the stability of systems. So in the Fourier transform we don't speak about the stability of systems, but in Laplace transform we'll see how one can determine the stability of the system. And also if you see the LTI system, in the Fourier transform we were using just j omega t and it was giving us the eigenfunction h of j omega e power j omega t. But why should we restrict ourselves to just j omega? So why should we restrict ourselves to just j omega? So we'll take the entire complex plane. So it is S equal to sigma plus j omega for all sigma and all j, because we already know that e power st is also the eigenfunction of LTI system. We get h of s e power st, and h of j omega was nothing but integral minus infinity to infinity h of t e power minus j omega t dt. So similarly h of s is again nothing but h of t e power minus st dt, right? So in other words, if you see, this is our Laplace transform. This was our Fourier transform. So if you see the relation between Laplace transform and Fourier transform, so if we substitute s equal to j omega in Laplace transform, we get Fourier transform, right? And also if we substitute s equal to j omega, like we replace j omega with s. If we replace j omega with s is equal to sigma plus j omega, in Fourier transform we get Laplace transform. So what does this mean? So if we have h of sigma plus j omega is nothing but integral minus infinity to infinity h of t e power minus of sigma plus j omega into t dt, right? So this we can write it as h of t e power minus sigma t e power minus j omega t dt. So this is nothing but our Fourier transform equation, right? So we can say Laplace transform is like Fourier transform of h of t e power minus sigma t. Again, it needn't be h, it can be x in general, any signal. It needn't be restricted to the impulse response of the system. Since we started our discussion there, I am continuing. But in general, it is true for any signal x of t. Now let us see an example. So example 1. So it is our familiar example only. So we have x of t is equal to e power minus at u of t. So first let us see the Fourier transform. We already know it is x of j omega is equal to 1 by a plus j omega and a greater than 0, right? Now let us see the Laplace transform. So Fourier transform, what did we have? X of j omega is nothing but integral 0 to infinity e power minus at e power minus j omega t dt. So in Laplace transform, what are we going to have? Integral minus infinity to infinity e power minus at u of t e power minus st dt. And s we can write as sigma plus j omega. So this is going to be again 0 to infinity because of u of t e power minus at e power minus sigma t e power minus j omega t dt. So now we can combine this minus a plus sigma t e power minus j omega t dt. Now if you observe, this is similar to this one, just it is multiplied by the factor of e power minus sigma t. So that is what we were discussing here, right? So now for this it's going to be same, just a is replaced with sigma plus a or a plus sigma. So it is a plus sigma plus j omega, and we have a plus sigma greater than 0. So if we were to write in terms of s, we have 1 by a plus s, and real of s is greater than minus a. So if you see here, this is valid, Fourier transform is valid only for a greater than 0, but this is valid for even a less than 0. Only that we need to take care of the sigma part, right? So this is required for the convergence. Hence this is called as the region of convergence. Since it is converging for real of s less than greater than minus a, we call it the region of convergence. And depending on a, the region of convergence varies, but we can find the Laplace transform even for negative a or 0, right? Which was not the case with Fourier transform, correct? Okay, and again to demonstrate the fact that we can get Fourier transform from Laplace transform by substituting s equal to j omega. If we have this x of j omega from here, right, then we get 1 plus a plus j omega, and the real of this is going to be 0, 0 greater than minus a, which implies that a greater than 0. So we got the Fourier transform, right? Okay, now let us see another example in Laplace transform. Example 2. So this example will demonstrate the fact that why this region of convergence is important. Okay, let's get started. So x of t is minus e power minus at u of minus t. So this is like a negative side exponential signal, right? So let us find the Laplace transform. It is given by x of t e power minus st dt. So this is nothing but minus infinity to 0 because it is u of minus t and we have a minus sign, e power minus at e power minus st dt. So this is nothing but this negative sign, we can use it to invert the limits. So it will be 0 to minus infinity e power minus at e power minus st dt. So this is nothing but 0 to minus infinity e power minus a plus s into t dt. Again this will converge for real of a plus s greater than 0. So this is nothing but e power minus a plus s into t by minus of a plus s from 0 to minus infinity. At minus infinity what happens? This goes to infinity, but what should happen for us? It should go to 0, right? So whatever condition we assumed was wrong. So this should be less than 0, right? So if this is less than 0, minus of a plus s will be greater than 0, and for minus infinity limit this value will tend to 0. Okay, so at last finally when we evaluate the limits we want the value to be finite. So for that we require this condition. So this will evaluate to 0 and for 0 it will evaluate to 1. So we'll get 1 by a plus s. And what we have here, real of s less than minus a. So does this result seem similar to you? Let's go back. So here also we got the same result, right? So to summarize, let me just write it here. So e power minus at u of t. We got x of s as 1 by a plus s, right? And what was the region of convergence? Real of s greater than minus a. Real of s greater than minus a, and e power minus at, correct? U of minus t. So for this what did we have? X of s is equal to 1 by a plus s. Again real of s we had less than minus a. So this algebraic expression is same. Expression is same. Only the region of convergence differs. So hence we can say that both the algebraic expression and the region of convergence is important. So both algebraic expression and region of convergence is important when stating the Laplace transform. Why? Because if I just have the algebraic equation, I'm getting like more than one signals, right? When I do the inverse Laplace transform, I'll get more than one signals. I don't know which one is correct. So I also need the region of convergence. So with the region of convergence, then my signal mapping will be 1 to 1. Okay. So both are important. And how do we represent the region of convergence? Representation of ROC. So we take an S-plane. We take S-plane and we plot or we shade the region of convergence. So S-plane, what it contains? It contains the real axis of S and the imaginary axis of S. And for our case, let's say this is 1 and 2. So for 1, what do we have? The region of convergence is real of s greater than minus a. So first let us find minus a. So let's say this is the line, real of s is equal to minus a. And for 1, what do we have? Real of s is greater than minus a. Greater than meaning all this region, right? So this region. This entire region without including the real of s equal to minus a region. So that's why we have put a dotted line. Otherwise we would have put a solid line. Okay. So for the second, what do we have? Real of s less than minus a. So that is nothing but this side, right? So this is for the second signal. So now let us look at another example. So example 3. So here we have x of t is equal to 3 e power minus 2t u of t minus 2 e power minus t u of t. So individually you know what values you will expect for the Fourier transform and the Laplace transform. So let us find them. 3 e power minus 2t u of t. Laplace transform I will represent by L here. So what you will get? The 3 factor will be same and you will get a plus s, right? And a here is 2. So you will get 2 plus s. And what will be the region of convergence? This signal is of the form this one, right? So the region of convergence is real of s greater than minus 2, right? For this case. So real of s greater than minus 2. And what about this signal? 2 e power minus t u of t. So its Laplace transform is nothing but 2 by 1 plus s. And what is its region of convergence? Real of s greater than minus 1. So when you combine these both signals, we need to take the region of convergence that is common to both. So let us see what happens. Like I'll again name it 1 and signal 2. So let us see the region of convergence for signal 1. We have real of s, we have imaginary of s, right? And this is real of s greater than minus 2. So let's say minus 2 is somewhere here. So what will this be? So this will be like this. All this region. Right? And what else we have? The second signal we have real of s greater than minus 1. So minus 1, let's say it's somewhere here. So what will this be? This will be this region. So which region is common to both? Common to both is nothing but real of s greater than minus 1. So when you combine and write, let's say s of s is nothing but 3 by 2 plus s minus 2 by 1 plus s, and your region of convergence is real of s greater than minus 1. Why it is like that? Because even if one of the signal diverging for that real value of s, for that sigma, then x of t will not be finite, right? The integral, the x of s will not be finite. So because of that, both of them should be finite in our region of convergence. So where that happens is where the region of convergence of the first and the second signal overlap. So even if you have n number of signals, you need to take the common region of convergence to all the signals. So if there is no common region, then we can say that the Laplace transform does not exist for that signal, which means that the Laplace transform equation is not converging. So this equation is not converging for any value of sigma. And of course you could have seen from this fact that Laplace transform is linear because we are taking the signals separately and finally subtracting them. So this also comes from the fact that it is like derived from the Fourier transform just by replacing S. And since the Fourier transform is as well linear, this is also expected to be linear. Anyway, we'll see this separately in the topic of properties of Laplace transform. So until then, hold on with me. Okay, so let us go and see another example. Example 4. So here we have x of t is equal to e power minus 2t u of t plus e power minus t cos 3t u of t. So here you can see it is like a decaying exponential with a cosine term, right? So we want to take the Laplace transform of this. So again we are familiar with the form e power minus at u of t gives 1 by s plus a. So now for this we can actually rewrite this. So a is not necessary to be real, correct? So a can be complex, but when we are taking the region of convergence, we only consider real of a. We need to replace a with real of a then. Okay, so by that case we have x of t as e power minus 2t u of t plus e power minus t e power j3t by 2 u of t plus e power minus t e power minus j3t by 2 u of t. So I have just decomposed this cos 3t in terms of complex exponentials. So now I can find the for each of them, like the Laplace transform for each of them. So this will give me 1 by s plus 2 and real of s should be greater than minus 2. And I have e power minus 1 minus 3j into t u of t. So Laplace transform of this will be 1 by s plus 1 minus 3j, and my real of s should be greater than real of 1 minus 3j, which is 1, right? And my e power minus 1 plus 3j into t u of t, its Laplace transform will be 1 by s plus 1 plus 3j, and again this is real of s is greater than, sorry, this is minus, so here also minus real of 1 plus 3j, which is minus 1 itself. So the common region of convergence is real of s greater than minus 1. It is similar to the previous question, so that I needn't draw it again. You can visualize it. So my final Laplace transform is nothing but sum of all these three. So 1 by s plus 2 plus 1 by s plus 1 minus 3j plus 1 by s plus 1 plus 3j. And I also have the by 2 factor. So I will have 2, 2. So either I can leave it this way or I can combine the terms and write it. So what will I get? I will get 2 into s plus 1 minus 3j into s plus 1 plus 3j plus s plus 2 into s plus 1 plus 3j plus s plus 2 into s plus 1 minus 3j, right, by s plus 2 into s plus 1 minus 3j factor of 2 into s plus 1 plus 3j. So if I try to evaluate this, what will I get? So this is like s plus 1 minus 3j into s plus 1 plus 3j. So it is nothing but s plus 1 whole square plus 3 square. And next I have s square plus 2s plus s plus 2 plus 3j into s plus 2. Again here I have s square plus 2s plus s plus 2 minus 3j into s plus 2. So this and this will cancel. Denominator, what will I have? I will have s plus 1 whole square plus 3 square, right? 9. Okay, so if I evaluate this, I'll get s square plus 2s plus 1 plus 9, which is 10, plus s square plus, so this I can add it up. So 2s square plus 4s plus 6, 6s plus 4 by 2 into s plus 2 into s square plus 2s plus 10. So this again 2 plus 2 I'll get 4s square plus, or I have a factor of 2 here, so I can cancel out 2. So then what will I get? S square plus 2s plus 10 plus s square plus 3s plus 2 divided by s plus 2 into s square plus 2s plus 10. So this is 2s square plus 5s plus 12 by s plus 2 into s square plus 2s plus 10. And real of my region of convergence is real of s greater than minus 1. So this is my x of s. So if you see in all of our examples we have considered so far, we have got all the terms in this form only, right? If we combine this again, we'll get some numerator polynomial by denominator polynomial. So all of them are like n of s is equal to n of s by d of s. N of s comma d of s are polynomial in S. So these type of Laplace transform are called as rational Laplace transforms. So mostly we'll be considering only these. Why? Because like our focus is on linear time invariant systems, and mainly they can be represented by the linear constant coefficient differential equations. And usually when you take the Laplace transform of differential equation, they come in this form, in the rational form. So it is important for us to analyze these class of signals. So we'll mainly focus on these. So now I'll introduce two terms called as zeros and poles. So zeros are nothing but location on S-plane where x of s tends to 0, and poles are nothing but location on S-plane where s of s tends to infinity. For example, if I have x of s equal to s plus 3 into s plus 1 divided by s plus 2 into s plus 4, or just let's say s plus 2. So then what I have at s equal to minus 3 comma minus 1, my x of s goes to 0, which means minus 3 comma minus 1 are my zeros. Similarly, at s equal to minus 2, x of s tends to infinity, correct? Because the denominator is going to 0, which means the entire expression will become infinity. So which means s equal to minus 2 is a pole. And also if you observe, if I tend s to infinity, what happens? So we get s in s by s. So it is dominated by s in the numerator. So numerator term is like s square, but the denominator is just s. So x of s itself tend to infinity. So we can say there is a pole at s equal to infinity. In general, we don't consider it because we are only interested in what happens in the finite S-plane. But you should also know that the number of zeros and number of poles are always equal, and if some poles are missing or some zeros are missing, then it means that they are present at infinity. Similarly, if you have the case where s of s is s plus 1 by s plus 2 into s plus 3. So in this case, when s tends to infinity, the denominator, it goes as 1 by s, which means s of s tends to 0. So you can say there is a 0 at infinity. So 0 at infinity, when it happens, if we take the degree, right? So first let me state what is a 0. We have n of s equal to 0, right? And pole is nothing but the denominator polynomial goes to 0. And we also have the degree of n of s and degree of d of s. So 0 at infinity occurs when degree of d of s should be greater or lesser. What happened here? Here the degree of the denominator is 2 while the numerator is 1. So degree of denominator should be greater than degree of numerator. Then there are zeros at infinity, and number of such zeros are given by number of zeros at infinity is equal to the difference between the degree of d of s minus degree of n of s. Similarly, for a pole to occur at infinity, what should be the case? So your degree of n of s should be greater than degree of d of s, and the number of poles at infinity will be given by degree of n of s minus degree of d of s. So in general, when they both are equal, there is no polar 0 at infinity. Again, coming back to the finite poles, the number of finite poles is given by the degree of d of s alone, right? Because if it is like x power 4, then you will have 4 solutions to this. So then your degree, like the number of finite poles becomes 4, and they can be repetitive. There is no problem with that. And the number of finite zeros is given by the degree of n of s, and say equal to. And usually in the S-plane, we can represent these poles and zeros because these are at values of s, right? So since s is the value here, you get s equal to 1, s equal to 2, and this kind of thing. We can represent it in the S-plane. So S-plane, what do we have? We have imaginary of s and real of s. So we represent the pole by x. So x represent poles, and zeros represent, or circles represent zeros. So if there are more than 1 zeros, we just circle like this. 2 zeros, we can say. 2 zeros at same location. So if you want to represent more than 1 pole at the location, you can just put an arrow and say 3 poles or so. That way. Okay. Usually you don't encounter it. So let us take one of our previous example and try to plot the ROC. Okay. Or let me only give you an example. So the Laplace transform is given by s plus 1 into s plus 3 by s plus 5 into s plus 6, and your region of convergence is given by real of s greater than minus 6. So how do you draw the ROC or the S-plane for this? So you have imaginary of s and real of s, and you have -1, or I'll take this as -1. So -1, -2, -3, -4, -5, -6, right? And what I have here, so I have the poles at -5 and -6, so I'll represent like this, and I have the zeros at -1 and -3, so I'll represent like this, and my region of convergence is something like this, right? S real of s greater than -1. So this is how I represent my region of convergence. So this is just an example, arbitrary example. In reality, this region of convergence needn't be the case. Arbitrary. For example. So we'll study more about this region of convergence now. So region of convergence of Laplace transform. Okay, so we'll see some properties related to this region of convergence. So the first properties is properties. So the first one is the ROC of x of s consists of strips parallel to the j omega axis in the s plane. So I'll write it down. The ROC consists of strips parallel to the j omega axis in the s plane. Why? Because we saw that it depends only on real of s, because only the exponent part is going to determine, not the periodic part of s, right? The frequency part of s is not going to determine the convergence. So if we say it is just with respect to real of s, then we are going to find it parallel to the j omega axis, right? If let's say s equal to -1, it is going to be like this, the entire omega. So that's why we get this. Or we can also say Laplace transform exists for signals for signal x of t, let's say, for which x of t e power minus sigma t is absolutely integrable, right? So we have this condition, e power minus sigma t. This is always going to be positive, so we can take it outside the absolute thing. This should be finite. So the property 1 states that the region of convergence depends only on the real part of S. So ROC depends only on the real part of S. Again, the second property is for rational Laplace transforms, which we saw, right? It is of the form n of s by d of s. The ROC does not contain any poles. Why it does not contain any poles? Because if it contains, then at that point the value of x of s will go to infinity, right? So we need to give that restriction. So s of s tends to infinity at the location of pole, which implies that ROC does not include that location. So what does this tell if there are poles here? So the region of convergence will not contain any of these points for any j omega. for any omega. For any omega, the points are not present in ROC. Okay. So using property 1 and 2, we can conclude this. Right, we can conclude this using property 1 and property 2. So now let us see the third property. If x of t is of finite duration, and it is absolutely integrable, then the ROC is the entire S-plane. So how can you say it is the entire S-plane? So what we want the region of convergence? So we need to find the sigma such that this is absolutely integrable. So let us take this. So for whatever values of sigma, if this is absolutely integrable, then we can say that those points are included in the S-plane. So for if x of t is finite duration and absolutely integrable, they are saying the ROC is entire S-plane, which means this is valid for all sigma, right? If we are able to prove this, then we can say this is true. So let us prove this proof. So let us assume x of t is non-zero in the interval t1 to t2. So this is going to reduce to t1 to t2. So this is equal to integral t1 to t2 mod x of t e power minus sigma t dt. So now I will take two cases. Case 1 for sigma greater than 0. So for sigma greater than 0, e power minus sigma t is going to degrade with time. So which means my e power minus sigma t1 is greater than e power minus sigma t2. And in general I can say e power minus sigma t1 is greater than e power minus sigma t for t belongs to t1 comma t2, right? So then I can replace this integral. So this I can say this is less than, because of this inequality, integral t1 to t2 mod x of t e power minus sigma t1 dt. So e power minus sigma t1 is now constant. So I can take it out. Integral t1 to t2 x of t dt. We saw this is absolutely integrable. So x of t is finite and this is also finite. So this entire value is going to be finite. So for case 2, so case 1 we saw that all the sigma greater than 0 are going to be valid. So we covered the S-plane for sigma greater than 0. So now let us see for sigma less than 0. Sigma equal to 0, we already know it is absolutely integrable. Sorry, it is absolutely integrable. So we know that this converges. So then what do we have for this? We have e power minus sigma t growing with time. So my e power minus sigma t1 is going to be less than e power minus sigma t2. And in general, e power minus sigma t is less than e power minus sigma t2 for t belongs to T1 comma T2. So even for t less than t1 it is going to be lesser, but we are only interested in this interval. So it is good enough for us if we consider this interval. So my mod x of t e power minus sigma t dt is nothing but t1 to t2 mod x of t e power minus sigma t dt, and this is less than t1 to t2 x of t e power minus sigma t2 dt. And again using the similar procedure, this is going to be a constant and it is finite, and this integral is also finite, so this is less than infinity. So for all sigma, the integral is less than infinity, so ROC includes the entire S-plane. Okay, so to visualize this, we can also see if you take any signal x of t, so t1 to t2, so it is having some, let's say it is multiplied with e power minus sigma t for sigma greater than 0. So it is going to change like this, right? So t1 to t2. So hence it is going to be absolutely integrable. On the other hand, if it is a growing exponential, e power minus sigma t for sigma less than 0, it is still going to be looking like this only. It will end finite value. So this integral is again going to be finite only. For any value of sigma or any t1, t2 if you take, it will never go to infinity. So for x of t is finite duration and absolutely integrable, we have the region of convergence as the entire S-plane. So next let us see what happens to x of t when it is of infinite duration, but it is equal to 0 for t less than some value. So in other words, x of t is like this. So for t less than t naught, x of t is equal to 0. So these kind of signals are called as right-sided signals. What about left-sided signals? We have this way, right? And this can start from anywhere. This point can start from anywhere. It needn't start from positive t naught. Okay. So here again t naught, and t naught can be anything. So for t greater than t naught, my x of t is equal to 0. So this is called as the left-sided signal. So now if I were to put an exponential e power minus sigma t for sigma greater than 0 or sigma greater than some sigma naught. Let's say for sigma naught, it converges. Okay, so I'll represent it in red color. Maybe I'll bring it to the center. So let's say for sigma naught it converges. So what it means? So this is e power minus sigma naught t. If I use this, then it is converging. Now multiplication of this with x of t. Now if I have e power minus sigma t for sigma greater than sigma naught, how will it look like? So I'll put it in blue. For sigma greater than sigma naught, it is going to decay very faster, right? E power minus sigma naught t decays faster. So it is also guaranteed to converge. Similarly here, it is the opposite. So if for sigma naught it converges, Okay, so let's say e power minus sigma naught t is something like this. So now for this to have a more decaying signal, then only it will converge. So for that condition, we want sigma to be less than sigma naught because it is in the negative direction. So it is guaranteed to converge. So we can again represent it mathematically like we did in the previous case. So before that, I'll state the theorems or the properties. So the fourth property is if x of t is a right-sided signal and if the line real of s equal to sigma naught is in the ROC. So we need this information, otherwise we can't say anything about it. Then all values of s for which real of s greater than sigma naught will also be in the ROC. So again, let us assume the signal is something like this. It starts from T1 and we know that we are given that mod x of t e power minus sigma naught t dt is less than infinity because it is absolutely integrable, because then only the sigma naught will be in the ROC. So now what we do, this is nothing but this is equal to t1 to infinity mod x of t e power minus sigma naught t dt. So we know that this is less than infinity. Now I want to find sigma 1 such that, or sigma such that this is less than infinity. So what I do, I just modify this a bit. T1 to infinity mod x of t e power minus, I multiply by e power sigma naught t and divide by or multiply by e power minus sigma naught t, right? So basically I'm multiplying by 1 and 1 I'm writing it as e power sigma naught t into e power minus sigma naught t. So e power sigma t into e power sigma naught t into e power minus sigma naught t dt. So this I can again combine these terms and write it as e power minus sigma naught t into e power minus of sigma minus sigma naught into t dt. So if I want this integral to be finite, this value should be finite. So for that I require sigma minus sigma naught should be greater than 0 because it is a right-sided signal and it is going to infinity. So my sigma should be greater than sigma naught. So once my sigma is greater than sigma naught, I can write e power minus sigma naught t is going to be greater than e power minus of sigma naught. This is less than e power minus sigma naught t into t1, because for t greater than t1 this is going to be having a lower value because this term is positive. It is going to degrade. So with this inequality, what can we write here? T1 to infinity, we can take this as less than mod x of t e power minus sigma naught t e power minus of sigma naught t1 into dt. And we can take this term outside and we get x of t e power minus sigma naught t dt. So both of them are less than infinity. So this term is less than infinity. Hence for this condition, we are going to have this x of t being absolutely integrable. X of t e power minus sigma t being absolutely integrable, which means the sigma is present in the ROC. So sigma greater than sigma naught is present in the ROC. So next, similarly for the left-sided signal, right? So we'll call it property 5. So if x of t is left sided signal, and if the ROC contains the line real of s equal to sigma naught, then all values of s for which real of s less than sigma naught will also be in the ROC. So for this you can derive it similarly. So we can derive similar to the above case. So you can go and derive and try and see. So anyway, moving on. So the next property is, if x of t is two-sided, then what happens? So if x of t is two-sided, so if it is right-sided, then I will have, let's say this is sigma naught, I will have all this, and if it is left-sided, I will have all this. If it is two-sided, then I can't say anything, right? So I will say that it is some strip, let's say some region of strip around sigma naught which is there in the ROC. So that strip can be 0 also, like it can only have the sigma naught as the only converging variable. So the strip itself can have the width of 0. So that is also possible. So if x of t is two-sided, and if the line real of s equal to sigma naught is contained in the ROC, then the ROC will consist of a strip in the S-plane that includes the line real of s equal to sigma naught. So you can see that any two-sided signal, right, can be decomposed into a left-sided signal xl of t and a right-sided signal, say same t naught xr of t. So if xl of t gives region of convergence sigma l, like if we know the sigma l is present, then if sigma l is here, then we know that the left side is going to be included in our ROC, right? So all this region will be included in my ROC. Similarly, for x r of t, we know that if it gives some xr, we know that if xr is included, then, or sigma r is included, then we know that the region of convergence is going to be everything greater than this sigma r. And my region of convergence for this x of t is nothing but this region, the common overlap. So it is like a strip. If sigma l is less than sigma r, then we say no region of convergence, and the Laplace transform does not exist for any values of sigma or any values of s. So from the last 4 properties, what can we conclude? We saw that for the finite signal, it is the entire S-plane. For the right-handed signal, it is the right-hand side of the S-plane, right? So for sigma greater than sigma naught. And for the left-sided signal, it is the left half of S-plane, right? From sigma naught less than sigma naught, sigma less than sigma naught, the entire left half, right? From starting from sigma naught, of course not from 0. And for the two-sided signal, we know it is like a strip. So what can we conclude from this? So the ROC must be, first is entire S-plane or the right half plane or the left half plane or the strip, right? Like a strip. So this is for if Laplace transform exists. Of course, if it does not exist, then it will not have any region of convergence. So my property 7 and 8 is exclusively for the rational Laplace transform. So my property 7, if the Laplace transform x of s of x of t is rational, then ROC is bounded by poles or extends to infinity. And we also know from property 3, right? So from property 2, there are no poles in the ROC. So there are also no poles in the ROC. So what it means is, if you have the S-plane and some poles, so your ROC either bounded between two poles. So let's say like this. So ROC is bounded between two poles or extends to infinity. What it means? So if you have the same three poles, so it cannot have this region and extend to infinity, because then it will contain the poles, right? So how should it extend to infinity? It should extend from the last pole. So then only it will not contain any other poles. So extends to infinity from the last pole, or it can also extend to minus infinity. So then the first pole is like considered. Again, by the same logic, it cannot start from anywhere from here, then it will include the poles as well. So extends to minus infinity from the first pole. So why this comes actually? So let's say each pole is represented by some signal, right? So some signal. And it can either be right-sided or left-sided or two-sided. Similarly for this also. So what happens if it is right-sided? You can see for each of the poles, let's say this is right-sided. Then what happens? Its region of convergence will be this entire thing. But we should also consider these two poles. Why? Because the region of convergence of sum of all these poles or in some combination is nothing but the common between all of the region of convergence, right? The common region between region of convergence of these separate signals. So we should also consider this. So if this is a left-sided signal, then its region of convergence will be something here. And you can see this is like the common region between these two signals. And what about this? So if this is a right-sided signal, then there will be no overlap. So right-sided implies no overlap, so no Laplace transform exists. So if it is left-sided, then it will have the same overlap as 1 and 2, right? 1, 2, 3. So ROC is like a strip between 1 and 2. So if I want it between 2 and 3, how do I get it? So I want this region, let's say. So for some signal, the ROC is this region. So what do you expect the signal to be? So the portion of the signal contributing to this first pole should be right-sided, because then only it will overlap here. And portion of the signal contributing to the second pole should also be right-sided. And the portion of the signal contributing to the third pole should be left-sided. So then only you will get this. If all the three are right-sided, then what will happen? It will just be this region, right? All are right-sided. Let me put it here. If all portions of the signal are right-sided, then what will happen? It will just be this, right? Similarly, for the left-sided, it will just be here, right? That I'm not writing it down. So this also implies that x of t itself is right-sided. Why? Because if all the portions are right-sided, then for some there exists some t for which t less than that t naught, it is going to be x of t itself is going to be 0. So x of t itself right-sided means its Laplace transform also has a right half plane, right? And the region of convergence includes the right half planes right to the rightmost pole, right? So it's the entire S-plane to the right of the rightmost pole. So that is our property 8. If Laplace transform x of s of x of t is rational, then if x of t is right-sided, the ROC is the region in the S-plane to the right of the rightmost pole. And if x of t is left-sided, then the ROC is the region in the S-plane to the left of the leftmost pole. So let us take a simple example. So x of s is equal to 1 by s plus 2 into s plus 3. So where are the poles located for this? So it is at -2 and -3. So this part of the S-plane is never going to be the region of convergence. So now we can have 3 cases, right, depending on the region of convergence. So we can get 3 different signals. So the first signal is like the region of convergence is this one. So this is case 1. And case 2, how do you get? We can get a strip, right? So if this is the region of convergence, then we get case 2. And for the third case, it is just the right-sided signal. X of t is a right-sided signal, which means the region of convergence is something like this. So this is again case 3. So here it is left-sided. This is two-sided. And this is right-sided. So based on the region of convergence, for the same algebraic expression, we can get 3 different signals. So we'll see more examples later on. Now let us see about the inverse Laplace transform. So we are going to derive the inverse Laplace transform from the inverse Fourier transform. So we already saw that the Laplace transform can also be represented as Fourier transform, right? So Fourier transform of the signal x of t e power minus sigma t. So which is nothing but integral minus infinity to infinity x of t e power minus sigma t e power minus j omega t dt. So then my x of t e power minus sigma t is nothing but inverse Fourier transform of this x of sigma plus j omega, right? And we know this inverse Fourier transform equation, which is nothing but 1 by 2 pi integral minus infinity to infinity x of sigma plus j omega e power j omega t d omega, right? So now we want to find x of t actually. So what we do, we multiply both sides by e power sigma t. So left hand side we get x of t and right hand side we get. So this is integration with respect to omega. So this is just like a constant for this. So we get e power sigma plus j omega into t d omega. So now if I attempt to replace this sigma plus j omega with s, then my ds is j d omega, or d omega is ds by j, and my limits of integration infinity will be nothing but sigma plus j infinity, and minus infinity will be sigma minus j infinity. So my x of t will be 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity x of sigma plus j omega, which is s e power st ds. So this is my inverse Laplace transform equation. So inverse Laplace transform. So what is my Laplace transform equation? It was integral minus infinity to infinity x of t e power minus st dt. So this is my Laplace transform. So this again you can see like it is the synthesis equation, and this is like the analysis equation, and x of t is like the integral of the weighted complex exponentials, and the integration is carried over a contour. So this is something called as a contour integral. This is for integrating in the S-plane. So you need to learn complex numbers and analysis of complex numbers to understand this. But anyway, for simple rational, or in case for all rational Laplace transforms, we no need to use this inverse Laplace transform. Why? Because we can just bring them to the form of, so if I have some x of s equal to some summation s bar n, am s bar n, m equal to 0 to n by summation n equal to 0 to, this m, let's say 0 to n, bn s bar n. So this I can write it in the form of partial fractions. So where I'll finally get it in the form like this, ai by s plus ai, right? Then for this I know the inverse Laplace transform, right? This is nothing but a e power minus ai u of t, or minus a e power minus ait u of minus t. Depending on the region of convergence, I will get these two. So if I'm able to map it, then I no need to do this, perform this integration and everything, right? This we already saw for few examples in the Fourier transform also. So this makes our lives very easier. So again, let us see one example. So if x of s is 1 by s plus 1 into s plus 2, and let's say real of s greater than minus 1. So first let us write it in the partial fractions form. We have s plus 1 by s plus 2. When I combine them, my numerator should be 1. So I can write it this way, because 2 minus 1 is going to give me 1. So now, depending on this region of convergence, I need to take the inverse Laplace transform. So I'll represent like this. So let me go to my S plane. I have imaginary of S, real of S, and I have poles at -1 and -2, and my ROC is this region. So it is a right sided signal, and both of these also should be right sided, which means they are represented by u of t rather than u of minus t, because u of t is right sided and u of minus t is left sided, right? I'll write it fully. So this will translate to x of t being e power minus t u of t minus e power minus 2t u of t. So this is my inverse Laplace transform of this function given this region of convergence. So if I have taken some other region of convergence, then this signal will also change. So that's it for today. We have covered about Laplace transforms, region of convergence, and the finally inverse Laplace transform. So go back and give it a read from the book, because it may feel like too much theory in a class. So it is always good to go back and revise. So in the next class, let us discuss about the properties of Laplace transforms. So until then, take